thanks to the moderators and organizing committee for allowing me to present our data. About a year ago, we started a new company called Genomic Prediction together with my co-founders Stephen Shu and Laurent Tellier. These are the smart guys on the team who developed some algorithms for polygenic risk scoring. And I'm excited today to talk about my role as well as the data that they've generated applied to the human embryo for the first time. And I think they brought me on because maybe some of you don't know me, but I've spent my career developing platforms for genetic testing in the human embryo. And today I'm going to talk about a new platform we've developed at Genomic Prediction. So just to remind everyone, what we currently do in terms of heritable disease is look at monogenic disorders. These are caused by mutations in a single gene. An example is cystic fibrosis. And the overall prevalence of single gene disorders estimated by the World Health Organization is 1%. When we think about polygenic disorders, these are things that we have to evaluate many thousands of positions in the genome. And this is an example of type 1 diabetes. And overall prevalence estimates of polygenic disorders in the population are 15 to 25%. So when we think about what we're doing in terms of testing for heritable disease, it's really the tip of the iceberg. And what we hope to do is expand testing to include polygenic disorders, which are more common. And we've been able to start thinking about this as a result of having large population-level data sets and genome-wide data from those individuals. This is an example that was published several years ago where you could predict the geographical origin of a person based only on their DNA. And at the time this was done, it was really based on relatively simple algorithms like principal component analysis. And of course, we've started generating large repositories of data banks on DNA from individuals. For example, the UK Biobank, we have 500,000 genome-wide data sets with established phenotypes to develop these polygenic risk scores from. There are other programs like the Million Veterans where we'll have a little bit more diverse population to develop algorithms for, and obviously this will be applicable to people from the United States, and again with several phenotypes that are commonly found. We're going to see a big growth, I think, in these repositories. Many people are talking about even bigger projects to generate large data sets. And I think we've seen a significant increase in publications and research around polygenic risk scoring. What I want to discuss is how do we predict variation in the population from DNA, in addition to having a clinical risk predictor. For example, with osteoporosis, fracture risk assessment is done in the clinic, and you can see that that only explains a certain portion of the variance in phenotype in the population. You may be familiar with genome-wide association studies. This is a one-at-a-time approach, and that can also be used to explain some of the variation, but it's really only with modern algorithms like the ones my partners have developed that we can start using, for example, machine learning to improve the ability to explain the variance in the population. And the interesting thing is that we can actually combine these things. So if you already have a known clinical risk, the polygenic risk score on the DNA, its predictive value improves. And we can also validate polygenic risk score algorithms developed on large data sets using out-of-sample validation on existing GWAS data from other populations. And that's kind of illustrated here that, for example, if you tested cholesterol and you did a polygenic risk score assessment, your ability to predict the disease is much higher. Of course, we don't have these types of predictors on embryos. We're not going to test their cholesterol or if they have a fracture risk. So what we use instead is family history, where we know that these diseases are more prevalent in families with history of that disease. This is the manuscript describing the algorithm that I showed you in the first slide. And what we did here was to evaluate, or what my group did was to evaluate whether or not we could predict height from the genome. And you can see it does a very good job at finding the actual height from predicted height. What we went on to do is ask whether or not we could rate siblings, which would be relevant to when we test embryos. And you can see you have a pretty good predictor for ranking which sibling is shorter or taller in that pair, depending on the size of the difference actually observed. And this often gets people worked up to think, oh, we're going to be testing for height. Actually, it's just because it's a common and reliable phenotype that we have a large sample size to train and ask whether or not the methodology is valid. And also in this situation, you could use this type of predictor for predicting idiopathic short stature. But again, really this was meant to validate the methodology. And the same method has been replicated by other groups, including a paper published in Nature Genetics. And in that paper, they suggest that we should begin contemplating inclusion of polygenic risk prediction in clinical care and discuss relevant issues. In that paper, they were able to apply the algorithm to predict several common diseases. And so our challenge was to then see if we could get the same kind of prediction from an embryo biopsy. And as I mentioned, I've spent a lot of time developing a platform. So this is a new platform we're calling expanded pre-implantation genetic testing, where we can test for 4 different factors from the same sample. One of the advantages is automated sample prep, which actually improves the ability to monitor QC. Initially, and when we submitted data for the abstract, we had 2 independent amplification methods from the same sample, which we performed in parallel in order to obtain information on genotypes for monogenic and polygenic disorders, and copy number for aneuploidy and structural abnormalities. We did further development to reduce this down to a single amplification methodology, and because we're able to run 96 samples in parallel and several of those in a week, we have a high throughput capacity with automated liquid handling. So it's a very convenient method to get all 4 tests from one platform. And again, the simplified protocol reduces QC burden, and the genotyping, having the genotyping in parallel, which we often don't do when we have copy number assessments, gives you the ability to evaluate more issues that you might have in the laboratory. And I've also spent a lot of time working with positive controls when developing new tests, and I think that's important for evaluating accuracy before clinical utilization. For copy number aneuploidy-based testing, we used 6 to 7 cells from samples with prior karyotyping for chromosome aneuploidy or euploidy status. We also looked at structural pgt-t, which is relevant to translocation cases where you have segmental imbalances, and again, we use cell lines with known segmental aneuploidies. For genotyping, we used cells from individuals with known delta F508 status, and this was one of the more difficult methods to find positive controls for, but in this situation, we used cell-free DNA from individuals with hypothyroidism that also had high TSH values, so clinical risk as well. So to show you some of the results, these are examples of copy number plots from 9 different cell lines, where you can see the expected abnormalities. And we convert this with our software to Circos plots for visualization. If we look at overall accuracy, in a sample set with 32% prevalence of aneuploidy greater than 99% accuracy. And we were actually surprised that we could get both copy number and genotyping from the same platform. So we're happy with this result, and we went on to test whether or not we could look at segmental imbalances. And again, we took cell lines with known imbalance. I can point here. But the plot shows copy number within the imbalance and outside the imbalance on the same chromosome. So you expect 2 copies outside the imbalance, which is shown in the blue box plots, and then the 1 copy or 3 copies within the deletion or duplication region. And we were able to detect an imbalance down to 3.5 megabases, and I think part of the reason we're able to do that is having over 900,000 SNPs evaluated. Now with genotyping, really what you need is something that potentially gives you equivalent accuracy to when you have a large amount of material like you might get from an adult. So we asked whether or not we got similar genotyping accuracy from limited quantities, like you might obtain from an embryo biopsy. And with imputation-based analysis, we do in fact get equivalent genotyping accuracy from an embryo biopsy level of DNA. So essentially, if you could do everything in the embryo that you could do on an adult with this genotyping methodology. For monogenic disorders, we have approximately 60 markers around several positions within a 1 million base pair window. You can expand that window out and look for crossover events. So there's a lot of things that you can do with this type of data, but one of those is to predict single gene disorders, like the delta F508 inheritance. In this sample set, we had greater than 99.9% accuracy. And then for polygenic risk, we looked at hypothyroidism. We were able to train on the UK Biobank 219,000 samples to develop a predictor that involved 4,945 SNPs. We applied it and validated it on an independent population, the eMERGE GWAS dataset, and again found equivalent prediction. We then evaluated the cell-free DNA using our protocol and again found good predictive value for a high risk of hypothyroidism. And if we look at that overall, we had about an 83% accuracy, which is actually higher than you expect based on the percentage of hypothyroidism that is genetically determined. This is a schematic just showing the overall results and how we might report it in 4 Circos plots. And we have several diseases that we're expanding into. So what I've shown you is the ability to combine machine learning algorithms with large data sets to develop predictors and molecular biology that allows you to get accurate analysis of all 4 of these areas in the pre-implantation embryo. It's the first method that can do all 4. And we think this will provide an additional embryo selection tool, increase utilization of IVF, and reduce incidence of common disease. In the IVF population, they have a higher risk of fewer embryos. In the general population, they may have a family history, but a greater number of embryos for selection, and we're invested in developing rigorous genetic counseling to support this. We're going to see much more in terms of publication and data sets available to expand testing to more disease. And I think if you look at the expanded carrier frequency field, what they're doing is really looking at monogenic, so that's another area that we could expand into more common diseases using this technology. And I'll thank the group at Genomic Predictions, Michigan State, and RMA of Connecticut. Thank you.
Thank you, Dr. Treff. My name is Alyssa Snyder. I'm a genetic counselor. You mentioned earlier on that some of the research that you do getting people worked up. I'm literally shaking right now. This is very triggering. We're not talking about curing polygenic diseases or treating polygenic diseases. We're talking about excluding embryos with these conditions. And the thought of, let's say you have a baby who will someday develop type 2 diabetes. Are you really going to say that that baby should never have been brought into existence? Because that's what we're talking about here, selecting embryos based off of these conditions.
Yeah, you kind of fed right into that. I have type 1 diabetes, so if my parents had our test, I wouldn't be here. So I've certainly thought about it. And I think one of the exciting things about this is, the potential use of CRISPR technology. So if my parents had CRISPR, I would be here without diabetes. So I agree it's something we need to discuss, but it's not that we haven't been discarding embryos for genetic disease for several years already. So I'm not sure it's a really big leap.
Absolutely, we're discarding embryos that we shouldn't have been discarded, and I think that's part of the major arguments against genetic testing is that we are excluding babies that could have been almost entirely healthy, and most of us in this room are not 100% healthy. So I think it's a big
no, I appreciate your perspective, and I do think several people have a similar perspective, but others don't, and I think it's important that people have an option to make that decision for themselves.
Dr. Coulier from Chicago made an already discussed of this yesterday in our personal discussion. But again, you
Thank
know,
you. Thank you for staying calm. I appreciate it.
Yeah. But, the point is that the life expectancy of some of the conditions that you call polygenic is very, very high, and now not different from the normal results the condition. So in many contexts like diabetes and other conditions. On the other hand, of course, as you know, with times, many polygenic disorders become monogenic. So the more we know about the condition, the more we'll be able to, in the future, make it direct diagnosis of monogenic disorder. So it should be taken into consideration.
Yeah, well, I disagree with your first comment. I think it's proven that people with polygenic disorders have a significantly reduced life expectancy, including type 1 diabetes, cancer. There was a talk earlier today where, actually yesterday in the prize paper session, showing that individuals with azoospermia die sooner from cancer than general population. So I'm not sure that that's a true statement. In fact, we have a lot of data showing there's a significant increase in life expectancy if you were to apply this technology to embryo selection.
Thank you. Unfortunately, we have to move on.
Thanks.
Thank you, Dr. Treff. The next